Good morning, guys. Today we're going to look at solving linear systems by substitution. Last lecture we talked about how multiple ways to solve linear systems. We looked at graphing. I talked about how it's not that great if you want exact answers. To be more precise, we need to use algebraic techniques like substitution or linear combination. So this lecture will focus on solving by substitution. As you can see here, we've got our steps for solving. To solve by substitution, solve one equation for one of its variables. So get it to y equals some expression, or x equals some expression. Could be b or c or z equals some expression. One variable solved to equal another variable expression, or an expression with the other variable in it. Then we're going to substitute that expression into the other equation and solve for the remaining variable. From there, we substitute that new number, that new value, back into the first equation where we've already solved and isolated a variable to get the second value for our linear system, the second coordinate for our points. So let's look right here. We're going to solve by substitution. So of my four variables, which of these looks like it's the easiest to isolate? Which one of the two x's or the two y's do you think would be the easiest variable to get by itself, easiest term to isolate its variable? Well, I'm going to say this x down here because it doesn't have a coefficient other than 1 on it. So to get it by itself, all I've got to do is move that y stuff over. So this is when substitution is a good idea to use. If I've got one variable that's sitting there already has a positive coefficient of 1, then I'm probably going to do a substitution because that's easy to isolate. If I've got numbers on all of them, I might use my other algebraic technique. But sometimes, even when numbers are on all of them, there are neat enough numbers to where you're not going to have to deal with a lot of fractions. Say you have all even numbers and you have a 2 as one of your coefficients. Pretty easy then to divide everything by 2, and now we can do an easy substitution. But we're going to use this x right here on the second equation. So step 1, get a new marker. Says take one equation, x minus 3y equals -3. Isolate one of its variables. So I'm going to keep the x. I'm going to move the 3y over. So x is equal to 3y minus 3. So I just solved one equation for one of its variables. Took this equation and isolated its variable. Second step tells me to take that expression, this expression, and plug it into the other equation. You can't plug it back into itself. That's obviously going to work. It would obviously go into itself. We want to see where it's equivalent in the other expression. So we're going to take the -2x plus 7y equals 10, and I'm going to plug in where there was an x. I'm going to replace it with 3y minus 3 plus 7y equals 10. So the x comes out, what x equals came in. So I'm just going to take this and substitute it straight in for the x. The -2 didn't change, the 7y didn't change, the 10 didn't change. X came out, replaced it with 3y minus 3 because x is equal to 3y minus 3. Now we just solve for y. See how we only have one variable left? Our remaining variable is y. So we're going to just go through normal equation solving steps. Distribute. So -6y plus 6 plus 7y equals 10. Combine your like terms. -6y plus 7y gives us 1y. And then isolate your variable. Move the 6. And 1y is just y, so y equals 4. So we get y equals 4. And we'll go to the last step. Substitute this new value back into this equation over here. So I know y is equal to 4, so it's going to go right back in over here where the y was, because I need to now know what x is. So step 3, x is equal to 3 times not y anymore. Now it's 3 times 4 minus 3. Clean that up a little bit so we can all see. Now you just evaluate. 3 times 4 is equal to 12, minus 3 is equal to 9. So x is 9, y is 4. Unless for now just write these as an ordered pair, 9, comma 4. So that's the point where these two lines intersect. I can always go back and check, like we looked at in the last lecture. How do I check to see if that actually is the solution to this system? How do I see if that is the one point where those two lines cross? Good, I will plug those numbers back in. So if we just did a little quick check, negative 2 times 9 plus 7 times 4, negative 18 plus 28 does equal 10. That checks. 9 minus 3 times 4, 9 minus 12 equals negative 3, so that checks. That point satisfies both equations. So we get to see how it's a lot more precise than what we did with the graphing. Okay, so this is always the best strategy if you need an exact answer. Let's look at another example though. Okay, guys. Right now I want you to pause this lecture just for a couple minutes. I want you to try to work this system by yourself and see if you can solve it by substitution. I'll just wait right here. Okay, so let's look at how we would solve this system. Pick a variable. I don't know which one you picked. I'd say the y is the best variable because there are two of them with coefficients of 1. Either one you want to work with, it's your choice. I'm going to go first equation. So let's say first step is solve one equation for one of its variables. So I'm going to take my first equation, 2x plus y equals 8. I'm going to solve for y by moving my 2x over. So y is equal to 2x plus 8. Step 2, take my other equation, the 3x plus y equals negative 2, and substitute that first expression into the other equation. So y is 2x plus 8, so I'm going to take out my y and replace it with 2x plus 8. From there, we just solve for the remaining variable. So I get 3x plus, there's nothing holding these parentheses on. There's no multiplication, so we can just drop them. If you need to, you can put a 1 there and distribute it. Combine your like terms. So I get 5x plus 8 equals negative 2. Move your 8. 5x equals negative 10. Move your 5. So x equals negative 2. Next step, after we've solved for one variable, substitute that back into the original equation. So let's see what we've got. Y equals 2 times negative 2 plus 8. And let's do the math, the arithmetic. Negative 4 plus 8 is going to be y equals 4. So y equals 4, x equals negative 2. So there should be my solution. Quick check. Negative 2 times 4 is negative 8. Nope. Got my point backwards. Very important you get them in the right order. X is negative 2, y is 4. So let's try that again. Negative 2 times negative 2 plus 4. Negative 2 is 4. 4 plus 4 is 8. That checks. 3 times negative 2 plus 4. 3 and negative 2 is negative 6. Negative 6 plus 4 equals negative 2. So that one checks. So that is our correct point. So that's solving by substitution. There's two special ones I want us to look at next. So I'll put them up and be right back. So here are the two special cases I want us to look at. So let's solve by substitution and see what's so special about it. First thing, pick a variable to isolate. None of them have a 1 for the coefficient. So you can really pick anything that you want. Just going to pick the x just to work with it. So we're going to take first equation, negative 2x plus 3y equals 6. isolate my x, I'm going to move my 3y. So negative 2x equals negative 3y plus 6. Move my negative 2. So I get x is equal to 3 halves y minus 3. So it's got a fraction in it, which is why substitution is not the best strategy, but let's still look at it because it does something special here in a second. Step 2, take that equation, plug it back into your other equation. So it's not 4 times x anymore, it's 4 times 3 halves y minus 3 minus 6y equals 6. So I took my 4x minus 6y equals 6 equation, and the x was replaced with 3 halves y minus 3. Solve for the y, so I'll distribute. 4 times 3 halves, 4 and 3 is 12, halves makes 6. 6y minus 12 minus 6y equals 6. Combine your like terms, 6y minus 6y actually cancels out. I get negative 12 equals 6. So at this point, I see my variables have canceled out. So I got x equals this expression for y. Well, my y's canceled out. So if I don't have y's, I don't have x's, I don't have any type of solution. So we at this point have to decide, is this a no solution or is this an infinitely many solution? So the question we ask ourselves, when does negative 12 equal to 6? Is negative 12 ever equal to 6? The answer is no. Negative 12 is never equal to 6. So it doesn't matter what x's and y's I put into this problem. I can never get a combination of x's and y's that will ever make negative 12 equal 6. Because they don't have any x's and y's in there to change them. They're constant. This will always be negative 12. This will be 6. They will never be equal. Since there is no combination of x's and y's that can make negative 12 equal 6, then we know that the answer is no solution. So as I'm going through doing a substitution problem, if my variables drop out and I'm left with a false statement like negative 12 equals 6, I have to say that there is no solution. Let's go back and look why. We knew no solution came from parallel lines. Well, these aren't the same numbers, so they don't seem like they'd be parallel, but go back and see if they're multiples of the same line. Negative 2 to 4, I need to multiply by negative 2, correct? So if I multiply by negative 2, negative 2, negative 2 gives me 4. That's okay. Now this would have to multiply by the same number. Is 3 times negative 2 equal to negative 6? Yes, so that right there tells me that they have the same slope because the x and y coefficients are multiples of each other. Now, is 6 times negative 2 equal to 6? No, it's not. That's 6 times negative 1. So they have the same slopes because they're multiples, but the constants aren't the same multiple, so they don't have the y-intercept. So that's why it is a no solution. They're parallel lines because they have the same slopes but different y-intercepts. Let's go over here and look at this example. Get this out of the way. As I go through, let's just solve for the same thing. You can see it's negative 2x plus 3y equals 6. Step 1. Negative 2x plus 3y equals 6. We already said that if we solve for x, it was 3 halves y minus 3. Plug that into our other equation. 4x minus 6y equals 12. Okay, so negative 12. So we've changed our equation a little bit. So again, 4 times 3 halves y minus 3 minus 6y equals negative 12. This is what x equals, so I substitute it in for x. Distribute 4 times 3 halves, 12 halves is 6, 6y minus 12 minus 6y equals negative 12. 6y's again cancel. Negative 12 equals negative 12. Once again, variables canceled out, but this time I'm left with a true statement. Negative 12 is always equal to negative 12. So what that tells me is there's infinitely many points, infinitely many ways I can combine x and y to get negative 12 to equal negative 12, because it doesn't matter what I pick, negative 12 is always going to be negative 12. So this would be an infinitely many solutions. Infinitely many solutions in that case. We don't get a one solution, they're infinitely many. Let's go and look back why. We multiplied by negative 2 to get negative 2 to be positive 4. This one was multiplied by negative 2 to turn 3 into negative 6. Here, to turn 6 into negative 12, did we multiply by negative 2? Yes, we did. So we can say the x's and y's were multiples of the same value, so we had the same slope. The constant was multiples of the same value, so you had the same y-intercept. And remember from the graphing video, same slopes, same y-intercepts, infinitely many solutions. I have a line that's negative 2 times longer. So it's the exact same line on both equations. That's solving systems by substitution. Pretty quick, pretty easy. I don't recommend using it if you're going to have fractions to have to keep up with, because it can get a little nasty there. But anytime I've got a coefficient of 1 on one of my variables, or if I've even got a variable or an equation where I already have one variable solved out, substitution is a pretty quick, pretty easy way to solve a linear system. And we don't have to do the guess and check like we did with the graphing. We get that exact answer pretty quickly. That's solving systems by substitution, and I will see you in class tomorrow, guys.